warning about the threat of a massive supervolcano eruption, like the one under Yellowstone National Park.
This supervolcano, which erupts roughly when it blows, it could destroy the United States as we know it.
Yellowstone National Park. Just the name conjures images of breathtaking landscapes, geysers shooting plumes of steam skyward, vibrant hot springs painting the earth in impossible colors, and vast forests teeming with wildlife. It's a sanctuary of natural beauty, a place that feels ancient and wild. But beneath this stunning veneer lies something far more powerful. Something almost unimaginable, one of the largest volcanic systems on Earth. Recently, subtle shifts and murmurs from deep within the planet have caught the attention of scientists. Is the sleeping giant stirring?
Natural systems can throw us a lot of curveballs. A lot of things can happen that we're not really ready for.
Let's journey into the heart of Yellowstone to explore the latest discoveries and understand the vigilant watch being kept over this geological wonder. But before we dive into the recent whispers from the Earth, it's crucial to understand the sheer scale and history of the volcanic titan we're dealing with. This isn't just any volcano, it's a supervolcano capable of eruptions far beyond anything witnessed in recorded human history.
Yellowstone supervolcano that is a continent killer, and it blows every 600,000 to 800,000 years, and everyone dies.
Yellowstone isn't marked by a single towering cone like Mount St. Helens or Mount Fuji. Instead, its power is hidden within a massive depression in the ground known as a caldera, essentially a giant collapsed crater left behind by unimaginably violent eruptions in the distant past. This caldera, stretching roughly 30 by 45 miles, is the remnant of catastrophic events that reshaped the continent. To truly grasp what Yellowstone is, we have to look back millions of years. Its volcanic history is written in colossal layers of ash and rock. The first known caldera-forming eruption, the Huckleberry Ridge Tuff eruption about 2.1 million years ago, was staggering. It ejected over 6,000 times the volume of material spewed out by Mount St. Helens in 1980, blanketing much of North America in ash. Imagine an event so powerful it dwarfs modern eruptions.
Mount St. Helens belched smoke and ash for 5 hours yesterday, then got hit with 2 sharp earthquakes early this morning.
Then around 1.3 million years ago, the Mesa Falls Tuff eruption created the Henry's Fork caldera, smaller but still immense. The most recent super eruption, the Lava Creek Tuff eruption, around 631,000 years ago, formed the Yellowstone caldera we see today. This event wasn't quite as large as Huckleberry Ridge, but still ejected about 1,000 cubic kilometers of material, enough to bury the entire state of Texas several inches deep. These weren't just eruptions, they were geological cataclysms. Understanding this history is key because the processes that drove these ancient events, a massive plume of hot mantle material rising from deep within the earth, melting the overlying crust, are still active today, feeding the system that powers the geysers and hot springs, and representing the potential, however distant, for future activity. This vast, restless system is the beast lurking beneath Yellowstone's undeniable beauty. Ground swells and earth shakes. While the massive eruptions are confined to the geological past, Yellowstone is far from dormant. It's a living, breathing volcanic system, and its breath manifests as subtle but measurable changes in the landscape and frequent seismic activity. One of the most critical indicators scientists track is ground deformation, the swelling and sinking of the caldera floor. Using high-precision global positioning system, GPS instruments anchored into the ground, and satellite-based radar interferometry (INSAR), researchers can detect changes in elevation down to the millimeter level. Over the past few decades, Yellowstone has experienced periods of both uplift and subsidence. For instance, from mid-2004 to 2010, the caldera floor rose at an unusually high rate, up to 7 centimeters, about 3 inches per year in some areas, causing significant scientific interest. Since then, the rate slowed and periods of subsidence, sinking, have also been observed. This geological breathing is thought to be driven primarily by the movement of magma and hydrothermal fluids deep beneath the surface. Magma intrusion or the pressurization of the hydrothermal system can cause uplift, while magma withdrawal or depressurization can lead to subsidence. Alongside this slow swelling and sinking, Yellowstone constantly trembles. The region experiences thousands of earthquakes each year, most too small to be felt by humans. However, they occur in distinct swarms, clusters of many earthquakes happening in a short period in a concentrated area. Notable swarms occurred near Madison Plateau in 1985, under Yellowstone Lake in 2008 to 2009, and near Maple Creek in 2017. These swarms aren't necessarily precursors to an eruption. They're often related to the movement of hot water and gases through existing fault lines or adjustments in tectonic stress within the crust, influenced by the underlying volcanic system. They are, however, a vital sign, indicating the dynamic and stressed nature of the crust above the magma chamber. These ground movements and earth shakes are the surface-level symptoms of the deeper processes constantly at work. Eyes and ears on the giant. Keeping tabs on a system as vast and complex as Yellowstone requires more than just occasional visits. It demands constant, high-tech surveillance. This is the mission of the Yellowstone Volcano Observatory, YVOS, a collaboration between the U.S. Geological Survey, USGS, the University of Utah, and Yellowstone National Park. They operate a sophisticated, multi-pronged monitoring network designed to detect even the slightest changes that might signal increased activity. The backbone of this network is seismic monitoring. Dozens of seismometers are strategically placed throughout the park and surrounding region, continuously listening for the faintest earth tremors. These instruments allow scientists to pinpoint the location, depth, and magnitude of earthquakes, tracking those telltale swarms and understanding stress patterns in the crust. Complementing these seismometers are the high-precision GPS stations we mentioned earlier, which measure ground deformation, the subtle uplift and subsidence with remarkable accuracy. This network provides a near real-time picture of how the ground surface is shifting, but the monitoring goes beyond just shaking and swelling. Scientists also keep a close eye on the gases escaping from the ground. Sensors analyze the composition and quantity of volcanic gases like carbon dioxide and sulfur dioxide being released from fumaroles and soil. As changes could indicate fresh magma rising closer to the surface. Thermal monitoring is another crucial piece of the puzzle. Satellites equipped with thermal infrared sensors regularly map ground temperatures across the park, looking for anomalies or significant changes in heat output from geyser basins and thermal areas. This is augmented by ground-based temperature measurements in key locations. Finally, the park's extensive hydrothermal system, its geysers, hot springs, and underground water network is closely watched. Changes in water levels in wells, stream flow rates, water temperature, and chemical composition can provide valuable insights into the heat and fluid dynamics beneath the surface. Recent years have seen upgrades and expansions to this network, incorporating more sensitive instruments, better data transmission, and refined analytical techniques, ensuring that YVO has the best possible eyes and ears focused on the restless giant below. Reading the volcano's pulse. Interpreting the constant stream of data from Yellowstone's monitoring network is a complex and often ambiguous task. There's rarely a single simple explanation for the observed phenomena. The ground uplift measured by GPS, for instance, could signify several things. It might indicate a small amount of new magma intruding into the existing reservoir deep below, causing the overlying rock to bulge slightly. Alternatively, it could be caused by the pressurization of the vast hydrothermal system, hot water and steam expanding and pushing the ground upward. It might even be related to the seasonal recharge of groundwater or subtle tectonic adjustments unrelated to magma movement. Similarly, earthquake swarms, while dramatic, don't automatically point towards an impending eruption. More often than not, they represent the crust adjusting to regional tectonic stresses, sometimes facilitated by the movement of hydrothermal fluids along pre-existing fault lines. These fluids can lubricate faults, making it easier for them to slip and generate earthquakes. Distinguishing between swarms driven purely by tectonic forces and those potentially linked to magma movement requires careful analysis of earthquake locations, depths, and the types of seismic waves generated. Changes in gas emissions or thermal output can also be tricky. An increase in heat or specific gases might suggest magma is nearer the surface, but it could also reflect changes in the plumbing of the hydrothermal system, opening new pathways for heat and gas already present to escape. The key challenge lies in separating the signals related to potentially hazardous volcanic processes from the background noise of this incredibly active geological area. Scientists look for combinations of signals occurring together. For example, significant uplift accompanied by specific types of earthquake swarms and changes in gas composition occurring in the same area. They also compare current activity to historical patterns observed over decades of monitoring. Even then, uncertainty remains. The system is vast, complex, and operates on timescales far longer than human observation allows. Therefore, while the monitoring provides invaluable insights, interpreting the volcano's pulse requires caution, continuous refinement of models, and an acknowledgement of the inherent ambiguities in reading the signs from such a powerful and deep-seated system. Mapping the magma maze. Understanding what's happening at the surface, the quakes, the ground movement, the steaming vents, is only part of the story. To truly comprehend Yellowstone's potential and its current state, scientists need to look deep underground to map the structure and condition of the magma reservoir system that fuels it all. This isn't easy. We can't just drill down miles into molten rock. Instead, researchers rely on indirect methods, primarily seismic tomography. Think of it like a CT scan for the Earth. By analyzing how seismic waves from distant earthquakes travel through the crust beneath Yellowstone, whether they speed up, slow down, or get absorbed, scientists can build a three-dimensional picture of the subsurface. Areas where waves slow down significantly often indicate hotter, partially molten rock. Recent, increasingly sophisticated tomographic studies have revealed a truly colossal system. It's not just one big blob of liquid magma. Instead, there appear to be at least two massive reservoirs stacked on top of each other. The shallower reservoir sits roughly 3 to 10 miles, 5 to 17 kilometers, beneath the caldera. This upper chamber is estimated to contain somewhere between 5% and 15% molten rock dispersed within a much larger volume of hot, solid but sponge-like crystalline mush. It's vast, perhaps large enough to hold the volume of 11 Grand Canyons, but it's mostly solid or semi-solid. Below this lies an even larger, deeper reservoir extending from about 12 to 30 miles, 20 to 50 kilometers down. This deeper chamber is estimated to be about 4.5 times larger than the shallower one and might contain around 2% melt. This deeper system is thought to be the primary source, fed by the mantle plume, which then intermittently supplies melt and heat to the shallower chamber above it. These findings are crucial. They confirm the immense size of the system, explaining the scale of past super eruptions and the vast amount of heat driving the park's hydrothermal features. But they also show that the upper reservoir, the one most relevant for potential future eruptions, is largely crystallized and not in an easily eruptible, melt-dominated state. Mapping this complex, multi-layered magma maze helps scientists understand the sheer scale of the heat engine driving Yellowstone and provides context for interpreting the surface activity being monitored. Steaming signals and hot water mysteries. Yellowstone's geysers, hot springs, fumaroles, and mud pots are arguably its most famous features, direct and dramatic manifestations of the immense heat source below. This sprawling hydrothermal system is incredibly dynamic, constantly changing, and provides another vital window into the volcano's behavior. Monitoring these features reveals fascinating patterns and sometimes raises intriguing questions. Steamboat Geyser, the world's tallest active geyser, provides a prime example. For years, it experienced long periods of dormancy punctuated by infrequent, towering eruptions. However, starting in 2018, Steamboat entered a phase of unprecedented activity, erupting hundreds of times with remarkable frequency, sometimes multiple times a week. While the exact cause isn't definitively known, this heightened activity likely reflects changes in the underground plumbing system, possibly related to subtle shifts in heat flow or pressure within the hydrothermal network linked to the deeper volcanic processes, perhaps influenced by recent earthquake swarms altering fluid pathways. Beyond individual geysers, scientists monitor broader changes across thermal basins. Variations in the temperature of hot springs, changes in the chemical composition of the water, like chloride levels or isotope ratios, and shifts in the boundaries of heated ground can all indicate adjustments in the underlying system. New thermal areas can emerge, while others might cool down or change character. These shifts aren't necessarily alarming. The hydrothermal system is inherently unstable, constantly reworking its plumbing. However, widespread, rapid, or unusual changes could potentially signal a disturbance related to deeper magmatic or tectonic activity. Tracking the discharge rates and temperatures of major rivers flowing out of Yellowstone also provides clues, as these waterways carry away a significant amount of the volcano's heat. Subtle, long-term increases or decreases in this heat outflow could reflect changes in the overall energy budget of the volcanic system. These steaming signals and hot water mysteries underscore the constant interplay between the deep heat source, the overlying rock, and the circulating groundwater, making the hydrothermal system a sensitive, albeit complex indicator of Yellowstone's restless nature. More than just the big one. When people think of Yellowstone erupting, the mind often leaps straight to the cataclysmic caldera-forming super eruption. While that's the ultimate potential hazard, it's crucial to understand that it's by far the least likely event to occur in our lifetimes or even over many centuries. Yellowstone poses other, more probable volcanic risks that deserve attention. The most frequent type of eruption is actually a hydrothermal explosion, also known as a phreatic eruption or steam explosion. These occur when superheated water trapped beneath the surface suddenly flashes to steam, causing a violent explosion that hurls mud, rock, and steam outwards, carving out craters. These are driven by the shallow hydrothermal system, not directly by rising magma. While much smaller than magmatic eruptions, they can still be dangerous locally, throwing rocks hundreds of feet and creating craters tens or even hundreds of feet across. Evidence of past hydrothermal explosions dots the Yellowstone landscape, including the large Mary Bay explosion crater on the shore of Yellowstone Lake, formed about 13,800 years ago. Smaller events happen more frequently, sometimes occurring without direct witnesses but leaving clear geological evidence. Monitoring changes in ground temperature, deformation around thermal areas, and seismic signals associated with fluid movement can help assess the potential for these steam-driven blasts, although predicting their exact timing and location remains challenging. The next most likely magmatic event, far more probable than a super eruption, involves relatively small lava flows. Since the last caldera-forming eruption 631,000 years ago, Yellowstone has experienced about 80 eruptions that produced lava flows or volcanic domes, primarily within the caldera boundary. The most recent of these occurred about 70,000 years ago on the Pitchstone Plateau. These eruptions involve thick, slow-moving rhyolitic or basaltic lavas. While a future lava flow would certainly be destructive within the park, covering land and potentially starting fires, it wouldn't pose a widespread threat beyond the park's boundaries. The precursory signals for such an eruption, intense localized earthquakes, swarms, significant ground deformation focused in one area, changes in gas emissions, would likely be much stronger and more obvious than the subtle background activity currently observed, providing weeks or months of warning. Understanding these more probable, smaller-scale hazards is vital for realistic risk assessment and preparedness within and near the park. The super eruption spectre. The term supervolcano carries immense weight, conjuring images of global catastrophe, and indeed, if Yellowstone were to experience another caldera-forming supereruption on the scale of its past events, the consequences would be devastating not just for North America, but for the entire planet. Such an eruption would eject thousands of cubic kilometers of volcanic ash high into the atmosphere, potentially covering vast swathes of the United States in thick ash layers, crippling agriculture, collapsing buildings, contaminating water supplies, and disrupting transportation and power grids for years. The sheer volume of volcanic gases, like sulfur dioxide released, would likely trigger a significant, albeit temporary, period of global cooling, often referred to as a volcanic winter, impacting ecosystems and food production worldwide. It's a truly terrifying scenario. However, and this is the critical point emphasized by scientists, the probability of such an event happening in any given year is exceedingly low. Based on the frequency of past events, 3 supereruptions in 2.1 million years, the average recurrence interval is roughly 600,000 to 800,000 years. Since the last one was about 631,000 years ago, some might mistakenly think we are due, but geological processes don't operate on strict timetables. Statistically, the annual probability of a supereruption at Yellowstone is estimated to be about 1 in 730,000, or 0.00014%. This is significantly lower than the probability of being impacted by a large asteroid. Furthermore, current monitoring data shows no signs whatsoever that such an event is imminent. For a supereruption to occur, a massive volume of eruptible magma, high melt percentage, would need to accumulate in the shallow reservoir, and there would need to be a significant trigger to initiate its ascent. Today's evidence suggests the upper reservoir is mostly solid mush, not poised for eruption. Any lead up to such a colossal event would almost certainly be preceded by decades, if not centuries, of intense precursor activity, dramatic ground uplift far exceeding anything observed recently, extremely powerful earthquake swarms, massive changes in thermal and gas emissions that would provide ample warning. So, while the specter is real in geological terms, it remains a very remote threat on human timescales.